Hello everyone, today we're going to learn about double integrals and polar coordinates. So let's first get into what is a polar region. So let me draw a picture to make this look a little better. So here, and then when are you going to want to use this? You'd want to use this in a situation where the domain is radial. And what do I mean by radial? So in the most simplest example, what we're talking about is if you have a circle, so say radius is r. Imagine that was what was on the xy plane and the surface is above this. So this would be a classic situation you'd want to do it. And here in this equation, x squared plus y squared is r squared. Or more generally, something maybe shaped like an annulus or a piece of an annulus. So this would be a piece of an annulus. And this would be on the xy plane with the z-axis coming out, and you'd have two competing radii. And something talking about how theta would be going from 0 to pi. So, and then as we're going through this on everything, we're going to have, we're about to do a change of variables. So the change of variables to deal with these kind of sort of circular type regions is always x is r cosine of theta, and y is r sine of theta. Alright, so what is this, what would be something more general than this, maybe just going after a segment, a sector here. Imagine going after just this part. So let's blow that up and take a bigger look at that, a closer look. So imagine some piece, so this would be what's called a polar rectangle. So first imagine an angle alpha, another angle beta, beta is bigger than alpha. You have the radii here, so imagine one of them is this, and it would continue around in a circular form. Call that distance right there A for the inner radius, and imagine then the outer radius, which then that you can imagine that swirling around, that being B. So this piece right here, which would be part of a bigger type thing, this is what's called a polar rectangle. So, and imagine that's on the xy plane, so this is x and y. The surface is above this, up in the air. So up in the air somewhere is where this surface is. So in a double integral, to give you an idea where this formula is about to come from, so let me get another piece of paper. So imagine, so for what does a double integral look like? So you would do the same thing. You'd cut this thing into a whole bunch of tiny little pieces to make an approximation. So let me write that out. So when we write the double integral, we would write, this would be the sum over say I equals 1 up to n. I'm going to take this to infinity anyway, so I'm just going to use the this, instead of writing an m, I'm just going to make it easier and take it to be n, because I'm going to take both these to go to infinity. You have your function, which represents the surface. Alright, and so the function did look like f of xy. My change of variables is x is equal to r of cosine of theta, and y is equal to r sine of theta. When I'm putting these in, there would be, so you'd have a test point inside here. So the test point would be just for a generic point, some generic point's going to look like ri star cosine of theta I star. That's the x value inside this little test point here, inside this little test subpolar rectangle. Then the other one, ri star sine of theta I star, is what you have for your y coordinate. So that's what's getting plugged in when I'm writing this right now. So I have ri star cosine of theta star, ri star sine of theta star, and then you have to multiply it by the area. So that's the height above this, and then the area of this tiny little polar rectangle has some area. So that's the actual area of this polar rectangle. We're talking about the surface above it, and then that's the height. Now, what is the area of one of these tiny little polar sectors? So what is this? Okay, so like let's just look at like blow that up a little bit bigger so we could stare at that. All right, so you might as well, let's see here. I'm just gonna actually go back to the other picture since it's written bigger. Imagine, like, and let's just use these same variables to keep it like as simple as you can. Like, what's the area of just this one right here? Okay, so the way that you'd find that the area of this is you'd compute first the area of this inner one, then the area of the whole bigger one going all the way out to here, and then subtract the bigger one. Like, take the big one and subtract off the little one, you'll get what's trapped inside there. So for the big one, so the bigger area, which that would be like this whole thing. If you have alpha to here, beta to there, this length is b. From just basic geometry, that thing is b squared over 2 beta minus alpha. The littler one, that smaller area, is the radial distance, which is a squared over 2, and then over whatever the length, the arc length is. So when I combine these two, if I want to figure out what this one is, just the area of that, you take the bigger one, which is the whole thing, and subtract off the smaller one, so that then our equation is the area of one of these is going to be b squared over 2 beta minus alpha minus a squared over 2 beta minus alpha. So that's the area of this polar rectangle right here. We can clean this up a little bit, factor out the common factors, and so you have b squared minus a squared over 2 beta minus alpha. Then you have b plus a over 2 b minus a beta minus alpha. All right, now this is what's going to play the role of, this is a midpoint. So if we were doing, like, if we wanted to take in this sum right here, basically these Ri stars, we could do this with the midpoint approximation, because we're about to take n to infinity, so it's going to fill out anyway. So what this is actually going to take the shape of is, this is going to be the R star, the tagged point in the partition, and then this right here, b minus a. B is this big line, A is this line right here. That's how the radius is changing, delta R. And then beta minus alpha, that's how the angular position is changing. So that's delta theta. So now when we insert this, that we have now that this is equal to the area of the polar rectangle, we now can conclude that this sum right here, we can insert that it's r star times delta of r delta of theta, so that now this equals the double sum f of r I star cosine of theta star Ri star sine of theta star multiplied by, this is what's coming in from the change of variables, delta R delta theta, I equals 1, j equals 1 up to n, and those are theta j's, sorry, theta j. Okay, now you take the limit as n goes to infinity, and then you pick up the double integral, where, so then you'd have f of r of cosine of theta, r sine of theta, now multiplied by r, dr d theta. Okay, now r goes from a to b, theta goes from alpha to beta. So this is the formula, and you can see, so what happened there was, going through this process, an extra factor showed up. That's coming from, we changed the variable. So this is a type of change of variables that we're doing here for dealing with things that are a function which is radial. We'll get back to more general changes of variables in a couple more sections, but for now we're just going to focus on this one. Okay, now given that that's where all these formulas are coming from on this page, so that's the change of variables gone inside there, and you always have to multiply it by the r. In this with this setting here, alpha and beta are the same as what I had before. So there was a line maybe here, this angle alpha, something over here that went further beta, and these can go all the way around, but I'm just putting them in this quadrant just for an example. And then we had two competing radii. The first one, that's the h of function r is equal to a function of theta, and then there was a bigger one that went all the way out to here. That was the second radius, h2 of theta. So that's what this whole thing is talking about here, the domain. And when you do it, you get this integral shape just like we derived here. And always this is x, this is y, and you always have x squared plus y squared is equal to r squared. So anytime integrals start having these kind of things in it, x squared plus y squared, it might be a good idea to go into this polar integration, like how this one right here is set up. So this has that form right inside of the cosine. Okay. So let's calculate this integral here. So first, try to draw the domain and try and figure out what are they talking about. What do I have to integrate this over? So R is the region in the first quadrant with circles with center at the origin and radii 1 and 3. So there'd be a circle here, radius 1, and another circle, a bigger one. And it would continue around. That one has radius 3. Alright, so then when I set this integral up, this would be a double integral. X squared plus y squared, as I mentioned, that's r squared. So cosine of r squared multiplied by this change of variables formula, r dr d theta. R goes from 1 out to 3. Theta goes from starting here on the ground at 0 up to pi over 2. Now this integral now is something very simply done by just a basic u substitution. But I want to comment on one thing to go through it a little faster. You can see that here, so this is that's the integrand. The integrand has nothing to do with theta right now as we speak. So when I do the integration with respect to theta, it's just going to be the length of that segment, 0 to pi over 2. So that right there handles the outer integration. Now you're just left with this simple Calc 1 integral, and you let u equals to r squared. du is 2r dr, and you get out of it through there. Alright, let's look at another example. Okay, something with the exponential function that in this situation it has negative r squared setting up inside there, because you want to think that if I factored off a negative, this is looking like negative r squared. Alright, So let's look at what is the domain here to try and figure out what the limits of integration are going to be. Okay, so it says D is the region bounded by the semicircle and the y-axis. Now it's kind of hard to figure out that that's a semicircle. So the way I actually want to think about it, imagine if I squared both sides of that. X squared is 4 minus y squared. Or x squared plus y squared is 4, which is 2 squared. And I'm just writing it like that so we can explicitly see what the radius is. Okay, so the radius is 2, not 4. Okay, so, and it's bounded by the y-axis, so then it must be this thing right here. So that's the circle. The radius here is 2. We need to integrate over this region right here. The domain's somewhere up here in the air. I'm sorry, the function is in the air, and the surface is in the air, this surface right here. We want to know what is the value, like what is the area under this curve, or it's going to be the volume in this situation of that function over this region. Okay, so as mentioned, that's e to the r negative r squared. So we have the integral e to the negative r squared, but the differential multiplied in r times dr d theta. R goes from 0 out to 2. Theta goes from minus pi over 2 all the way up to pi over 2. Alright, and just like the previous example, this integral right here, there's no dependency on theta inside here, so I can just easily clean up this integral as the integral for theta is just the length of this this distance right here that it travels over. So with respect to theta, this since there's no thetas inside here, it's just this length, which is pi. So end answer right now is pi times, not end answer, sorry. The next line is pi 0 to 2 e to the minus r squared times r dr. And then again, you're at a Calc 1 integral, and you let u equals to r squared. And you'll bump that out and be able to finish the integral in just a second. Alright, let's see another one here. Okay, so now we have something that looks a little more complicated. I mean, it's not so clear what we need to transform these this change of variables to, like what is r going to go between and what is theta. So the first thing would be to figure out what does this domain represent here. This says that y goes from 0, going from the inside to the out, y goes from 0 up to square root of 9 minus x squared. And it says x goes from minus 3 to 3. Alright, and just like before this one, it's a lot easier to look at this if you square both sides. You're going to have y squared is equal to 9 minus x squared. You will get to x squared minus y squared is 9, or 3 squared. So now let's draw a picture and figure out what's going on. Alright, y goes from 0 up to this function. Alright, so the function goes from 0 up to this function. X goes from minus 3 to 3. So as y varies from 0 to the function, what we're looking at here is this upper semicircle. So that's what we have to integrate over for this change of variables. Okay, so and remember, and I'm about to insert in here, x is r cosine of theta, y is equal to r sine of theta. Alright, so now the double integral is, alright, so I will have 3 times r cosine of theta plus 4 times the quantity r sine of theta squared multiplied by r dr d theta. Here r is the radius, it goes from 0 out to 3. theta spins from at 0 all the way over to pi. Alright, so now that's the integral to compute. Okay, let's start going after this one a little further. Okay, so here, so now this definitely inside here, this integrand depends both on theta and r, so I can't do anything like just like I did before, just calculate the integral with respect to theta in a very simple form. So I have to actually explicitly figure it out. Okay, so this is, let me clean it up just a little bit. 0 to pi, 0 to 3, and yet multiplying the rn, you'll have 3r squared cosine of theta plus 4r. So here I have an r squared, another r shows up, and I'm about to have r cubed. I'm going to eventually have to deal with, this is going to be sine squared. And the only way, well, not the only way, the best way to deal with like something with sine squared and an integral is what you're going to want to use is a double angle formula. So the double angle formula is 1 minus cosine of 2 theta over 2. So inserting that for the sine squared, 1 minus cosine of 2 theta over 2, that allows me to get rid of the square on there. And then now I'm at dr d theta. Alright, at this point this integral is just going to be a little bit tedious. You're just going to have to go through it one by one. First you're going to do the integration with r and then theta. I'll take it just a little bit further. Okay, so doing the integration with respect to r, I have 3, and remember theta is a constant when I integrate with respect to r. So I would have, for this one right here, r cubed over 3, and I'd have to evaluate that from 0 to 3. Then, actually let me just do the whole, well, okay, that's for that one. Now plus, let me clean up, that's going to be 2 times 1 minus cosine of 2 theta, r to the 4th over 4 from 0 to 3. Then after all this gets done, I still got to do d theta on this. Alright, luckily the lower limit is 0, so when you evaluate it at that, it's going to be 0. This number here is going to be 27 when you got 3 cubed, and then it'd be 27 divided by 3. This number here is going to be 3 to the 4th, which is what is it, 81. So then, and then you just finish it off from there, and then it's going to be simple integrations, which is cosine, a single value of just a constant, and then a double angle formula, which is just really easy to compute. You just do u equals 2 cosine theta. Alright, let's look at one more example here. Alright, volume of the solid inside this sphere, and then outside this cylinder. Okay, so what is this domain, like what are we about to integrate over and what's happening? So first let me draw the sphere. Okay, so that's x squared plus y squared plus z squared is 16. Radius is 4. Alright, now it says inside this there's a cylinder. X squared plus y squared equals 4. So that's, I want to think of that as 2 squared. So radius on that thing is 2. Alright, so what is inside here is like a cylinder. So something like this. Cylinder is inside there, and it wants me to get the volume of the solid inside this sphere, but outside that cylinder. So it's like a ball with a hole in it is about what I'm about to integrate over. Okay, so when I look down, when I do a projection onto the xy plane, I'm looking at something like this. So that's if you were standing right on top looking straight down. This is what you're about to integrate over. So in the radii here is, you have an inner radius of 2 and an outer radius of 4. Theta is going to go from 0 to 2 pi. Now, what is it that I'm supposed to integrate? And how do you set up this function here? All right, so what I want to do is, so volume of the solid inside the sphere. Okay, so what is like inside this sphere but outside of that cylinder? Okay, so what I want to do is think about like a cap going over this, because like this is on like a cap being on top of it, and that would be the upper part, and then there's a lower part too. So on the upper part, so just focusing on the upper part, you have this upper part of this ball here. You cut out this middle part here, so there's like a hole cut in it. Alright, so the surface that is above this right here is actually coming from here. Alright, and if I have to solve that for z, I would have z equals 16 minus x squared plus y squared, and then but I would take a square root to isolate the z. Okay, now there's two branches. Which one do you take, and how to get through this? If you take the positive one, it's going to be the upper part. The negative one will be the lower part. So that what I'm going to do when I'm setting up this integral, I'm actually just going to, by the symmetries of this shape, not exactly as I've drawn it, but like if I would have drew it perfect, this is supposed to be a perfect sphere. This top part, this is going to have volume same part as the bottom. So I'm just going to double, I'm going to do the top part, double it, and that's how I'm going to not have to deal with like these two branches of this. So what I mean is this double integral is about to be 2 times, all right, this function square root 16, and I'm inserting for x squared minus y squared, that's minus r squared. Now that thing times r, dr, r goes from 2 to 4, and theta spins around from 0 to 2 pi. All right, and just as before, there and on some of the earlier examples here, there's no dependency on theta, so the integral with respect to theta is just the length of that segment, which is 2 pi. So then I have 2 times 2 pi times this integral 0 to 4 square root of 16 minus r squared times r dr. Now we're back again at a simple Calc 1 u substitution integral. So you just let u equals 16 minus r squared. du is minus r dr. That will bump out that r. And maybe just for practice to remember how changing these limits of integrations go. When I plug in 0 on this, 0, you're plugging in 0 for r. 0 gets mapped to 16. The number 4, you put in 4 right there, 4 goes to 0. So now this integral, constant in the front, 4 pi. I pick up a negative symbol from this. Then I have square root of u, so I'm going to write it like u to the 1/2. That r cancels. du goes from 16 up to 0. Now, from there, I think everybody could finish it off. And if you want, you could get rid of this negative symbol. You could flip the integral so it would be positive, going from 0 to 16. If you don't want to do that, you don't have to, and just remember that you have the negative out front. And that's it for the polar integration. So this is the beginning of the change of variables stuff that we're going to start slowly moving towards. There'll be one more other one where we can actually explicitly go after it with the geometric formula, and then eventually it'll turn into, there's the big picture. It's always going to have some change of variables, and something has to sit here because you did it, and it's just going to be something different given a different type of setting. And that's it. I hope everybody has a good day. Thank you very much.